we'll move on towards the last half of the second chapter, which is basically dealing with the energy conversion efficiencies. Uh, Efficiencies basically they are very frequently used in thermodynamics, and it basically indicates that how perfectly you are basically converting your energies as a result of the heat transfer or work done on the system. So it basically determines how well you uh, transfer or convert one form of energy to another form, and this basically determines the performance of your system. It is basically defined by, over here it is written output, but this would be essentially input. So performance or efficiency is basically measured by the required input and desired output. So it is basically how much of the input that you have given to a system you are able to extract out of that energy that is being given to you. Is the point clear to you?
Yes, sir.
All right. Um, let's say I go to market and I ask for a water heater, which is an electric water heater. An electric water heater, you know, is basically operating on electricity. And the seller or the salesperson tells me that the electric water heater has an efficiency of 90%. Now, this brings a question in my mind that normally electrical energy is converted into thermal energy completely. That means there is a 100% conversion of electrical energy into thermal energy. So why is that once I go and ask for an electric water heater, the salespersons give me an efficiency of 90%? Is that? Can somebody comment on that?
Because the energy dissipation when the electricity flows in the wires, this may be the reason.
Yes, that may be the reason. Normally, it is assumed that electrical energy converts 100% to the or almost 100% to the thermal energy. In electric water heater, what you are essentially doing is that you are heating up the water by using electricity. Clear?
Yes, sir.
Is it clear so far?
Yes,
All
sir.
right. So, all right. So once the issue is once your electricity or electric power is 100% transferred to the water in form of thermal energy, water has to get to the tap or water has to get to the desired location. There is energy loss from the water to the surroundings as a result of temperature difference between the water and the surroundings. So essentially this 10% loss is associated with the energy transfer from the water to the surroundings. Clear enough?
Yes, sir.
It says that the
Yes.
ratio efficiency of the heater is basically the ratio of the energy delivered to the house by the hot water as compared to the energy supplied to the water heater. Clear enough?
Yes, sir.
All right. Now,
Yes, sir.
all right, great. So this is about the electric heater. You also have heaters which are working on natural gas. And if you go and ask for the efficiency of such heaters which are based on, let's say, natural gas, the salesman tells you that the efficiency of such a system is, let's say, 55%. So there is a need to understand that how the energy is being, the source of energy defines the efficiency of the system. Uh, this brings me to the concept of combustion efficiency or efficiency associated with the combustion process. Whenever you're talking about combustion process, you understand that there is a fuel involved, all right, whether it's petrol or whether it's diesel or whether it's natural gas, there is some fuel which is associated with the combustion process. Is this point clear?
Yes, sir.
Yes, sir.
Yes, sir.
All right. And the capabilities of a fuel is basically, or the energy content of the fuel is basically defined by heating value. Heating value basically defines what is the maximum amount of energy that can be extracted out of that fuel. We'll look at the specific definition of it also, but heating value basically defines the maximum amount of energy that can be extracted out of that fuel once the fuel is being burned. And the amount of heat released during combustion is the actual amount of energy that is being drawn out of that fuel when it undergoes the combustion process. So the combustion efficiency is basically the maximum that you can draw out, which is the heating value of the fuel which is being burned, to that of the amount of heat released during the process. Is this point clear?
Yes, sir.
All right. Now, how do we define the heating value of a fuel? Heating value of the fuel is being defined as the amount of heat released when a unit amount of fuel at room temperature is completely burned and the combustion products are cooled to the room temperature. So this is the heating value of the fuel that you can extract at maximum. Gasoline would have its own heating value, diesel would have its own heating value, similarly petrol would have its own heating value. Heating value is basically the amount of heat released when a unit amount of fuel at room temperature is completely burned and the combustion products are cooled to the room temperature. Let's say the heating value of gasoline is 44 kilojoules per kg. This means that when 1 kg of gasoline is completely burned at 25 degrees centigrade and the products or the combustion products are leaving the system at room temperature, this is the amount of energy that I'll get out of it. Ideally, whether I'll get this amount of energy or not is dependent upon whether I am burning it at room temperature or whether the combustion products are cooled to the room temperature or not. So this is the maximum that I can get, which is depending upon the heating value, and the actual that I get is basically uh, some portion of it, which basically defines the efficiency of the combustion process. So far, is it clear?
Yes.
Right. Moving on, we have two kinds of heating values. The lower heating value. The lower heating value is when the water vapors leave in the form of vapors. They are leaving the system after the combustion process. They leave the system in the form of vapors. Whereas higher heating value is when the water vapors or when the water, which is a combustion product, it is completely condensed. It is leaving the system in the form of liquid, and the heat of vaporization is also recovered. Uh, is this point clear to you or not? Should I elaborate more on it?
सर रिपीट कर दें एक बार ये
All
वाला
right.
पॉइंट.
I'll give you an example. Let's say I have gasoline having 1 kg and it is being burned at 25 degrees centigrade. And the combustion gases that I have, it contains carbon dioxide and water. And the water which is leaving the system is leaving in the form of vapors. All right. Energy released in such a case would basically be the lower heating value of gasoline. This means that what do you when water in liquid form, when water converts to water vapors, do you require energy or is the energy released?
Require energy.
Sorry,
Require energy.
you require energy
To
to
convert
convert
water into water vapor
water
we require
vapors. Yes,
energy.
yes. So if it is leaving in the form of water vapors, that means these water vapors have already consumed some amount of the heat so that they convert it from water to water vapors. Clear? Is it clear?
Yes, sir.
Had it been the higher heating value would have been more or less than the lower heating value.
Less.
Sorry,
ज़्यादा होनी चाहिए सर.
it would be more. Why? Because higher heating value would have lower heating value plus the energy required to convert water into water vapors. because that energy would not have been used in the case of higher heating value, because the water would be leaving in the form of liquid. So the energy required to convert water into water vapors would not have been used in higher heating value. So that energy, higher heating value, would be more than the lower heating value. Is the point clear to you?
Yes.
All right. Now, we have looked into the energy of the combustion process. Now we'll look into the thermal efficiency of a power plant. How thermal efficiency is the ratio of net shaft work output of turbine and the heat input to the working fluid. Let's see how a power plant works. In a power plant, you have basically three major components. One is the combustion process, in which there is fuel coming into the system, which has, let's say, a higher heating value, some higher heating value that basically donates the or represents the energy, which is kilojoules per kg for the fuel which is entering. And as a result of the combustion process, there would be some heat released. So there would be some heat released as a result of this process. Is this clear?
Yes, sir.
And the combustion efficiency would be what? The combustion efficiency would be Q, which is released, or the power released, divided by the higher heating value multiplied by mass flow rate. Why I have written? Because I have written heat in the form of power over here. If I have to express the higher heating value in the form of power also, what I'll do is that higher heating value is energy, which is kilojoules per kg, multiplied by mass flow rate, which is kg per second. So essentially I would have kilojoules per second, which is power or kilowatts. Clear enough? Is this point clear? So the combustion efficiency would be the heat released per unit time divided by higher heating value multiplied by the mass flow rate. Is this point clear to you?
Yes, sir.
All right. In a plant, the second component is where you have a turbine. What does the turbine do? It takes up the energy that is being released from the combustion process. So this energy which is coming out of the combustion process is being taken up by the turbine, and as a result, turbine is rotating. That means it produces a work, or which is known as shaft work. So this heat is being used to rotate the turbine to produce the work, which is the shaft work. Clear enough? Is the point clear?
Yes, sir.
All right. So this is basically the efficiency related with the turbine is basically the thermal efficiency of the turbine of the power plant. So the thermal efficiency is what? Thermal efficiency is essentially the what is the input? Heat coming from the combustion process is the input, and what is extracted out of it? It is the shaft work which is extracted out of it. Clear enough? This is the thermal efficiency, the net work output divided by the heat input to the working fluid. Clear enough? Is this point clear?
Yes,
Yes,
sir.
sir.
All right. Now the third component in a power plant is essentially the generator, which is generating the electricity. So how is this working? The shaft which is working, it becomes the input for the generator, and the electrical work is basically the output of the generator. Is it clear? So the efficiency of generator would be, what is the input for the generator?
Mechanical work.
Yes.
Shafts, mechanical work.
All right, great, very good. The work of the shaft, and what is the output? Is the electrical
Electrical
Electricity.
power.
electrical power coming out of the system. Clear? Is this point clear to you?
Yes, sir.
All right. So the overall efficiency of your power plant would be what? It would be the overall efficiency would be the efficiency of combustion multiplied by the efficiency of the turbine, which is the thermal efficiency, multiplied by the efficiency of the generator, which is the efficiency of the generator. And if I write down these components over here, this is the efficiency of your combustion process multiplied by the efficiency of your turbine, which is shaft work divided by the heat that is being provided to the system, multiplied by the efficiency of the system, which is electrical work produced divided by the shaft work for the generator. And if you see, the shaft work would cancel out. Sorry. The shaft work would essentially cancel out. The heat would essentially cancel out. So what you are left with is basically the electrical work that you are taking out by of the fuel multiplied by the mass flow rate. So this is the overall efficiency of your power plant. Is this point clear to you guys?
Yes, sir.
All right. So what is a generator? A generator is a device that converts mechanical energy into electrical energy, and the efficiency of generator is basically the electrical power output divided by the mechanical power input. And if you see the overall efficiency of the power plant, it is basically the product of combustion efficiency, thermal efficiency, and the generator efficiency. And this comes out to be the net electrical work output per unit time divided by the higher heating value multiplied by the mass flow rate, so that both the values are energy per unit time. Is the point clear? I hope it is clear to you.
Yes, sir.
All right. Moving on. Normally, the efficiencies of automotive engines, which are based on petrol or gasoline, it is somewhere between 26 to 30%. For diesel, it is 30 to 40, 34 to 40%. And for large power plants, it is about 40 to 60% of the heating value or heating value of the fuel that is being used. Uh, Moving on, we'll now consider the efficiencies of mechanical and electrical devices separately, and then we'll try to figure out the combined efficiencies of mechanical and electrical devices. What is a mechanical device or energy of mechanical device? The transfer of mechanical energy in mechanical devices is usually achieved by a rotating shaft, and it is often referred to as shaft work. Now, there are two kinds of devices with regards to shaft work. One is basically pump or fan, which receives the shaft work in the form of electric motor and transfer it to the fluid as mechanical energy. Whenever I would be referring to pump in this chapter, pump basically would comprise of pump, fan, or compressor. And when I'm talking about the increase in the mechanical energy of a system or increase in the mechanical energy of the fluid, pump basically means the increase in the mechanical energy of the fluid by changing its elevation. Fan basically refers to the increase in mechanical energy of the fluid by increasing its velocity, and compressor basically refers to increasing the mechanical energy of the fluid by increasing its pressure. So all the three categories in which the energy of the fluid is increased, whether it's pump, fan, or compressor, I'll refer to the term as pump. Is it clear?
सर पंप क्या कहते क्या चीज इंक्रीज करेगा?
Pump.
पंप
आपका पानी का पंप जो the water pump that you have at your home, what does it do?
ठीक है, पुल वाटर ही करेगा ना?
वाटर पुल करता है, वाटर की एलिवेशन इंक्रीज करता है ना. So a
Yes.
pump basically increases the elevation of the fluid
ठीक है
by
सर
increasing the
सही है
mechanical
सर
energy and by giving velocity, and compressor by increasing pressure. So but in all the three cases, you have a shaft work which is associated. A shaft work basically transfers energy. The rotation of the shaft basically transfers energy to the fluid by increasing its mechanical energy. And how the mechanical energy is increased? It could be in the form of elevation, which is Z. It could be in the form of velocity, which is V, or it could be in the form of pressure, which is P. All the three components can contribute towards the increase in the mechanical energy of the fluid. Clear enough?
yes sir
All right. But on the other hand, what a turbine performs is turbine converts the mechanical energy of the fluid. It utilizes the mechanical energy of the fluid to do the shaft work. It is doing the opposite process. That means it is extracting the energy of the fluid, moving fluid, to rotate the shaft. So it is doing exactly the opposite of what is being done in the case of pump. Clear enough? Is the point clear?
yes sir
All right. Moving on, the mechanical efficiency of a device is basically defined by the mechanical energy output. This is the output that you're getting divided by the mechanical energy input. E mechanical out over E mechanical in, or you could also express as 1 minus the E mechanical losses over E mechanical in. So this is the fraction which is lost. 1 minus that would give you the efficiency of your system. Clear?
yes sir
All right. Now, as I mentioned earlier, that the effectiveness of the conversion process between the mechanical work supplied in the case of pumps, fans, or compressor, which I'll refer to as pump, or extracted. Extracted means taken out from the fluid in the case of turbine. These would give you the pump efficiency and the turbine efficiency. So we'll look at these efficiencies separately. Pump efficiency is basically increasing the mechanical energy of the fluid. So you are increasing the mechanical energy of the fluid. How? By providing mechanical energy input as a result of shaft work. So you are rotating the shaft in order to increase the mechanical energy of the fluid. This increase in energy could be in the form of height, pressure, or velocity. So you refer to it as the rate of change of the mechanical energy of the fluid divided by the work shaft in. That means the energy required to rotate the shaft is your input, and how much of it is being converted into the increase in mechanical energy of the fluid would give you the efficiency of the pump. Or it could be also written as the work pump useful. That means the useful work that is being extracted out of the total work which is being done on the pump would give you the efficiency of the pump. So far, is it clear?
सर मतलब है कि जितना शाफ्ट वर्क ज्यादा होगा उतनी ज्यादा हमें मैकेनिकल एनर्जी उसकी मिलेगी सर
जितना शाफ्ट वर्क ज्यादा होगा, but आप you look at this point, let's say the shaft work, that the work done to rotate the shaft is, let's say, 30 kilojoules. All right. And the change in mechanical energy of the fluid in an ideal case where your efficiency is 100% would be 30 kilojoules. Otherwise, it would be less than 30. All right.
यस
Is the
सर सही है
point clear?
यस
All right. Change in mechanical energy of the fluid, what is meant by it? It is meant by the mechanical energy of the fluid leaving the system minus the mechanical energy of the fluid entering into the system. So if before entering into the pump, the elevation was, let's say, 5 meters, and after the fluid leaves the system, let's say the efficiency or the height of the fluid, or the height of the fluid attained by the height attained by the fluid is, let's say, 15 meter. So the change in mechanical energy of the fluid would correspond to a height of 10 meters. Clear enough? In cases of a pump.
यस सर क्लियर
In the turbine, it's exactly the opposite. In turbine, what you are using is you are extracting the energy of a fluid. So mechanical energy, decrease of the fluid is your input, and the mechanic and the energy required to rotate the shaft would be your output. That means the energy produced by the turbine would be your output, and the energy required as the input or the energy of the fluid, uh, energy decrease of the fluid would be the your input. Is this point clear?
सर एक बार रिपीट करते हैं फिर से ये टरबाइन वाला.
All right, turbine. Uh, how do you rotate a turbine? You apply pressure onto it. Pressure rotates the turbine. So a high pressure steam enters into the turbine, start rotating it, and leaves the turbine at low pressure. All right.
जी
So,
सर.
so the pressure of the fluid which is required to rotate the turbine would essentially decrease. That means the energy of the fluid would decrease as it enters and leaves the turbine. And as a result, you will extract some amount of that energy would be extracted out as as a result, which is in the form of rotating shaft. Clear enough?
Yes sir.
So change in mechanical energy of the fluid is your input, and the rotating shaft is your output in cases of turbine. That means the work of the turbine, which is extracted out of the fluid, E means extracted out of the fluid, is your input. And out of that extracted work, the amount of work produced in terms of rotating the shaft is your work output from the turbine. Clear enough?
Okay sir.
If there's confusion, I could elaborate it again.
सर ये दोबारा बता दें फार्मूले का जो ई होने में ये क्या बता रहा है?
अच्छा मैं बता देता हूँ. आप you have understood that the fluid would give its energy to run the turbine. Is this clear?
Yes sir.
All right. Now the portion of energy it gives to run the turbine, some portion of it would be used to rotate the shaft. All right.
Yes sir.
So work shaft out means the energy. This is the input. That means the energy extracted out of the fluid. This is your input. If your turbine is a ideal turbine, let's say the efficiency of the turbine is 100%. That means whatever energy is extracted out of the fluid would be used or would be provided in rotating the shaft. Clear?
Yes sir.
But in case it is not ideal, it's a 90% efficiency turbine. Let's say the energy extracted from the fluid is 100 kilojoules. The energy transferred to the shaft would be what? 90 kilojoules. Clear?
Yes sir. Yes sir.
Right. Now here work turbine or work having a dot, the power of turbine is meaning the work of the turbine that it is actually producing. And this work of turbine with E means the energy extracted out of the fluid. So this is the one which was extracted, and out of this extracted, this this one represents the actual work which is being produced by the turbine, the rotation of the shaft. Clear enough?
Yes sir.
ये नहीं क्लियर है दोबारा बता देता हूँ.
Clear है sir.
Alright, I'll explain it once we move on to the next slide. Also, we'll have this again. So change in mechanical energy of the fluid. It's written with the absolute sign. Why? Let's say the fluid entering into turbine is at high pressure, and the fluid leaving the turbine is at low pressure. So the change in pressure would give you a negative value. All right. You have a turbine
Yes
over
sir.
here. There is fluid entering into a turbine at high pressure P1, let's say 5 megapascal, and it is leaving the system at let's say P2, which is 2 megapascal. The energy extracted out of the fluid would correspond to how much pressure?
3 megapascal.
3 megapascal would be extracted out of it. But if I write it in terms of energy, I would have the absolute form of it. All right. I would have the absolute form of the mechanical energy entering as a form of mechanical fluid. This means that this would be a positive quantity, and essentially the efficiency of the turbine has to be a positive quantity. So out of that, let's say 3 megapascal, 2 megapascal is being supplied to the shaft. So that means your efficiency would be somewhere around 66%. Clear enough?
Yes, sir.
All right. Moving on, motor is a device which is used. You must be aware that motors are normally used with pump. And what is motor doing? It is basically giving in the electrical energy to rotate the shaft. Clear? So the efficiency of motor would be work electrical in or work shaft out divided by the work electrical in to the system. Clear enough?
Yes, sir.
Similarly, the generator is a device which provides electrical energy as the output, and mechanical and shaft work input or mechanical work input is the is the required input. Required output is work electricity out. Now, you know that normally motors are used with pumps. So if I have a combination of motors and pumps, or if I have a combination of motor and pump, this is the efficiency of motor. The efficiency of a pump is what? What is the efficiency of a pump?
Change in energy of fluid divided
Sorry,
by input
sorry.
power. In energy of fluid divided by input power.
All right. Yes, you have increase in the energy, mechanical energy of the fluid divided by the work shaft into the system. So essentially, work shaft in is equivalent to work shaft out. So a motor and pump combination would have essentially change in mechanical energy of the fluid divided by the work as the efficiency of the combination. So a pump motor efficiency is basically what? It is basically the electrical energy or the fluid and the energy of the fluid which is being increased as compared to the electrical energy as the input. So the amount of energy provided to the pump motor in the form of electricity would be your input, and your output would be the change in energy of the fluid. Clear enough? The overall efficiency. The overall efficiency of pump and motor as a combination. Is it clear to you guys?
Yes, sir.
Similarly, if you have a turbine generator, what you'll have would be exactly opposite. Electrical work output would be your desired output, and your input would be the change in mechanical energy of the fluid. The change in mechanical energy of the fluid would give you the input to the turbine, and electrical work output would be the output that is desired from the turbine generator combination. The shaft work, which are common in generator and turbine, would essentially cancel out in the couple. Clear enough? I hope it is
Yes,
clear to you
sir.
guys. All
Yeah.
right. Uh, the efficiency of turbine is, let's say, 0.75, and the efficiency of generator is 0.9797. So the overall efficiency of the system would be the product of the two, which is 0.73. So we'll quickly go through the example to understand how these efficiencies are being implemented. It says that a water in a large tank is to be used to generate electricity by the installation of a hydraulic turbine generator. So a turbine and generator at a location where the water depth is 50 meter. Water is supplied to the turbine at 500 kg per second. The power produced by the generator is 1862 kilowatt, and the generator efficiency is given to you 95%. you have to determine the overall efficiency of the turbine and generator. And if you look at the overall efficiency for turbine generator, work electricity out is given to you. What you have to determine the change in mechanical energy of the fluid, which is basically associated with which component? It is associated with turbine. I have this schematic in front of me. It says that the turbine is placed over here and it is placed next to the generator. The output of generator is this much power. You have to determine the overall efficiency, which is sorry, which is dependent upon the change in mechanical energy of the fluid as it moves from state 1 to state 2 through the turbine. So the mechanical energy of the fluid is dependent upon what? The moving fluid has three components of energy. It is the flow work, which is pressure divided by the density, plus it is dependent upon the kinetic energy, plus it is dependent upon the potential energy. So if I see over here, from state 1 to 2, the change in kinetic and potential energy is almost negligible, is almost zero. So energy which is entering into the turbine, which is E1 minus E2, would give me the change in mechanical energy of the fluid. And it would be essentially dependent upon E in minus E out, which is dependent upon the flow work, pressure divided by the density minus the pressure at the exit, which is zero. Is it clear so far? Is the point clear?
सर ये पहली इक्वेशन फिर से एक्सप्लेन कर सकते हैं, ये जो काइनेटिक एनर्जी एंड पोटेंशियल
जी 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 कर सकते हैं. If you recall the mechanical energy change in, I'll take you to the slide. You remember this slide? Change in mechanical energy of the fluid, this last slide. Change in mechanical energy of the fluid, it is dependent upon what? Mass flow rate entering into the system and change in mechanical energy per unit mass, which is essentially this flow energy, this kinetic energy, and this potential energy. Clear?
Yes, sir.
So for the turbine, these two terms are essentially zero because there's no mention of the velocity and the elevation. They are almost zero for the turbine. The important thing is change in the pressure, which would give you the change in mechanical energy of the fluid. Clear enough?
Yes, sir. Understood.
So let's go back and see how we can apply this equation. So let's try to apply this equation. This is my state 1, this is my state 2. I know that change in mechanical energy of the fluid is basically mass flow rate multiplied by uh, P2 minus P1 divided by the density. Is this clear so far?
Yes, sir.
All right. Also write this P1, which is atmospheric pressure over here. P1 is the atmospheric pressure, clear? Sorry, P2 is the atmospheric pressure. Is it clear?
Yes, sir.
And P1 is what?
Fluid.
P atmospheric plus rho GH at this point. Is it clear?
Yes, sir.
So if I write over here mass flow rate multiplied by P2, or P2 is, let's say, P atmospheric minus bracket P atmospheric plus rho GH divided by the density. This would cancel out, and I would essentially have mass flow rate multiplied by GH as the change in mechanical energy of the fluid. Is the point clear?
Yes, sir.
Any doubts in this? I hope it is clear. So the change in mechanical energy of the fluid is essentially, per unit mass is essentially GH, which comes out to be 0.491 kilojoules per kg. And if you move on, the total change in mechanical energy of the fluid, absolute value, would be the mass flow rate multiplied by E mechanical in minus E mechanical out, which is 5000 kg per second multiplied by the specific energy change. This is the change in mechanical energy of the fluid. Now, if you have to calculate the overall efficiency of the turbine, you will apply the formula, which is work electrical out. This is given to you, divide by change in mechanical energy of the fluid. So the overall efficiency comes out to be 0.76. In the case, you have to find the efficiency of the turbine. Now, how can you find out the mechanical efficiency of the turbine? You know
Energy
that the
efficiency, right?
overall, sorry,
जनरेटर की efficiency से और electrical power given है.
or in other words, you know that the overall efficiency is efficiency of turbine multiplied by efficiency of the generator. This efficiency given to you. You have calculated the overall efficiency. This is the only thing left. So you can the overall efficiency generator, you'll get efficiency of the turbine. Clear? Is this point clear to you? Yes, no, are you there? Are you not there?
Yes, sir, clear.
Yes, sir.
All right. So the efficiency of the turbine would be essentially the overall efficiency divided by the efficiency of the generator. This would give you the efficiency of the turbine. And once you know the efficiency of the turbine, you have to calculate the shaft power supplied by the turbine to the generator. And what is the formula? The formula for turbine efficiency is the work shaft out divided by the change in mechanical energy of the fluid. You already know change in mechanical energy of the fluid. You have calculated the efficiency of the turbine. You just multiply the two and you will get the shaft work extracted out of this much energy of mechanical fluid. Clear? So I'll stop over here.